Okay, dear students, the last lecture ended abruptly because there was some problem with my phone. Okay, let's continue from where we left, as I keep saying all the time. Okay, we were doing this theorem. We said that for every smooth function k, there exists a unit speed plane curve with sine curvature as the given smooth function k. And furthermore, if we had another plane curve with the same sine curvature, then the difference between the first curve and the first would be the obtainable from a rigid motion from some rotation and some translation of the original curve or the first curve. They are the same, they're just different in their orientation in space, as I explained earlier. Now in the proof of the theorem, we have got to a point where we found that this new curve alpha tilde at s can be written like this: s naught to s, it has two components, plus some vector alpha tilde at s naught, which is a constant vector, and of course then phi tilde of s, where phi tilde is the angle with which this alpha curve, the phi tilde is the angle which the unit tangent of this new curve alpha tilde makes with the x-axis. Okay, now if it is the angle that it makes with the x-axis, which is a fixed vector in our plane, then the sine curvature must be d, the derivative of this phi tilde with respect to s. And since we are assuming it to be the given function ks, then it must be equal to ks, from which after differentiation we get this. But this is the same thing as phi. This is how we had defined our original phi of s, was this integral s naught to s ku du. So this is just phi of s plus this theta, this constant, this number theta. So we substitute it here, and remember that we have to substitute it in this equation where we have phi tilde of t. Here we have phi tilde of s. So phi tilde of t would be phi of t plus theta. So we just substitute it in the equation 1, and we get alpha tilde at s, this new curve, this other curve which has the same sine curvature as the first one, should be s naught to s cos of phi of t plus this fixed vector theta differentiated with respect to t, then s naught to s sine of phi of t plus theta, which is a fixed number, dt, plus some fixed vector a, where this a vector is nothing but r tilde, or not, alpha tilde at s naught. Okay, now this is what we have. Now we have to show that it is the rigid motion of the original curve, right? So then this is cos of a plus b, and this is sine of a plus b. I just apply the trigonometry. Cos of a plus b is cos a cos b minus sine a sine b, and sine of a plus b is sine a cos b plus cos a sine b. So I can write it as s naught to s cos of course this is the first component, cos of phi t into cos of theta minus sine of, let me write it, minus sine of phi t into sine of theta. Theta is fixed, remember that, of course, dt, then comma s naught to s, of course, sine phi t cos of theta plus cos phi t sine of theta, of course, whole thing differentiated with integrated with respect to t, plus this vector a. Okay, is it coming inside? Yeah, now it's okay. Okay, now this can be written further as, because differentiation is with respect to t, and theta is a cos theta sine theta are constants, so I can just write it as cos of theta s naught to s cos phi t dt minus, of course, sine theta out, s naught to s, of course, sine of phi t dt. This is my first component. Then, of course, here cos of theta into s naught to s sine phi t dt plus, and you take the sine theta out here, s naught to s, what do I have, cos of phi t dt, and then I have here it's a comma, so this is the first component, this is the second component, it lives inside R2, plus this some fixed vector A, right? Now if you know the formula for rotation in a plane, this is nothing but the rotation of the point s naught to s cos phi t dt, comma, s naught to s sine phi t dt plus this vector A. I mean to say this whole expression is nothing but the formula for rotation by theta of this vector. If I rotate this vector by theta, I would get this. Now it basically comes from, and perhaps an earlier formula that you might have done, the formula for the rotation inside a plane. If I have, so let us do that, because once we do that, we have shown that new curve is the what we call, so let me write it first here, where r theta is the transformation of, is the rotation by theta of the plane, of the whole plane R2. Now I want to actually give you an idea why that would be the case. If you have any point here AB, right, any vector AB in R2, and you rotate it by some angle theta in the counterclockwise direction, and you get another point, let's call it A dash B dash. Then this new point, the rotated point, and if I say the rotated point, when I rotate this AB, I would get, say, A dash B dash. Then it can be evaluated that A dash B dash is always equal to cos theta into A, let me write it, A cos theta minus B sine theta. Let me write it properly. This rotation of AB with the angle, by the angle theta in R2 would be A cos theta minus B sine theta, and of course then the other one would be, what is that? It is B cos theta plus A sine theta. So this is the formula for rotation. This is what I have used here. In place of A and B, you have got s naught to s cos phi t and s naught to s sine phi t. If you rotate it to theta, you will get this expression. So this expression is basically the rotation of this vector by an angle of theta. Now you can easily think, if you think of a vector in R2 in terms of a complex number, then you must know that r theta is nothing but multiplying e raised power I theta to the complex number a iota b. So if you evaluate this, so r theta of AB in terms of complex numbers is nothing but this thing, and if this is your A dash plus iota B dash, then you just, from this formula you will get this formula. You just multiply, e raised power iota theta is basically cos theta plus iota sine theta. Just multiply both sides and you just equate real and imaginary parts. You will get A dash is equal to this and B dash is equal to this. Very easy. Okay, so this is where we have reached. So I can think of from this, where we have gotten to till now, I can write this alpha tilde at S is nothing but MA vector into R theta vector of S naught to S cos phi t dt, comma, S naught to S sine phi t dt. Right? Where MA is now the translation of this vector by MA is translation. Translation is just addition in terms of vectors. Translation of R theta, this thing, whatever this is, by A. Okay, so this is a composition. Now what we have got, alpha, which is nothing but m of alpha at s, where m is the rotation of alpha. Now this expression is the expression for the original curve alpha of s, and this m is the translation followed, the rotation followed by the translation of the original curve, this vector. Okay, so therefore we have shown that this alpha tilde of s is obtainable by some rigid motion of the original curve. It means that if basically the the plane curve is uniquely determined up to a rigid motion by its sine curvature. Now that would be the second part of our theorem if we not paraphrase it in this way. Okay, now furthermore, now since there was a bit of confusion here whether it was R. No, I have used in my notes and that your study material, I have used the alphabet R to represent the curve, and in here I am doing the alphabet alpha, so I will revert to alphabet R to make it easier, but you should be able to understand that you're now PG students, so it shouldn't make any difference how we denote a certain function, whether we denote it by alpha or R. It shouldn't make any difference, but just to make it a little easier, not to complicate things, sometimes I write alpha and R. I would stick now to R. So but that shouldn't make a difference. Okay, now let's come to another theorem, and then we will come back to our curves in R3. We are in curves, we're talking about plane curves right now, the sine curvature. Now there is this small theorem. Now let me denote it by R from here onwards, because I saw the study material that you have got. I have used the letter R. If R is a unit speed curve, but it shouldn't make a difference, I think, unit speed plane curve, then n sub s, the unit normal, the unit sine normal that we talked about, is equal to minus k sub s times t. You must remember how we defined our unit subnormal. Now if you have a plane curve, I've got this unit tangent vector t, right? Then if I rotate it in anticlockwise by pi by 2, I get this n sub s. Okay, then we defined our sine curvature, since we know that t dash is perpendicular to t because it is a unit speed curve, right? And therefore t dash is parallel to n sub s. And then we define basically, what was that? When we defined our sine curvature, I forget my formulas. Okay, it was this k, what was this? We'll go t dash is equal to minus k sub s times ns. This was our definition of sine curvature. Okay, now we are saying this n of s is basically minus k sub s times the unit tangent vector t. Okay, and you know that k sub s is the sine curvature and t is our unit tangent vector to the curve R. Okay, now let's forget alpha for the time. Okay, now proof of this theorem is, we know that t is perpendicular to n sub s. So t dot n sub s should be equal to 0 because they are perpendicular vectors. And if I differentiate both sides with respect to s, so I should have t dash dot n sub s plus t dot ns dash should be equal to 0. Which means, but t dash is ks, the sine curvature ks, with times the n sub s vector. So I can write here k sub s, n sub s dot n sub s is equal to minus t dot n dash sub s, the derivative with respect to the arc length s. Okay, now this is a unit vector. N sub s is a unit vector, therefore its dot product with itself would be equal to 1, and I would get k sub s is equal to minus t dot n dash sub s. So this is what we have thus far. Let's call this equation 1. Okay, now we know that n sub s is a unit vector, right? Now n sub s is a vector, a unit vector, or a vector of fixed magnitude. Therefore, it must be perpendicular to its derivative. So that means n sub s must be perpendicular to n dash s. But also t is also perpendicular to n sub s, and all these vectors live inside a plane, right? Now in a plane, if one vector is I have got a vector which is perpendicular to two other vectors, then those two vectors must be parallel, right? So it means that n dash s and vector t must be parallel vectors because they are perpendicular to the same vector. If in a plane, this won't be the case in R3. This is for R2. In a plane, if I've got a fixed vector and two vectors are perpendicular to the same vector, then they must be parallel. Therefore, this vector must be parallel to t, which means n dash s must be equal to some alpha times t, where alpha is some scalar because they are parallel vectors, right? But n dash s, as we take dot product of both sides with respect to t, I will get n dash s dot t is alpha times t dot t. Now t is a unit vector because I have got a unit speed curve. So that means that alpha must be equal to n dash s dot t, right? But as we already know, from equation 1, t dot n dash s, and it's a commutative thing, so it's the same thing as n dash s dot t is equal to minus ks. So alpha must be equal to minus k sub s, and from which we get, you just substitute the value of alpha here, you will get what we had to prove, that n dash s is equal to minus k sub s times t. So this is what we had to derive. And then there are certain exercises that I highly recommend that you do them yourself so some I have done in the notes, some you do yourself. And we now go back to the space curves, the curves in R3. Now we just leave this sine curvature here and we move ahead. There are certain things that you will do by yourself from your study material. Okay, it's easy now. I don't think it's difficult. There's going to be any difficulties here. Now let's come back to our space curves. That means I used to the alphabet, as I said, I'm going to now use the alphabet R to denote a curve. Now a curve would be a function R from an interval AB closed, semi-closed, let me write it, R from an interval I to R3. So we're going to come back to our R3, right? And we can, if it is a regular curve, we can always choose a parameter, especially we can choose arc length to be our parameter, then it becomes a unit speed curve, right? So I've got R at s is a unit speed curve if I choose my parameter to be the arc length s. So t, my unit tangent, is r dash. Now this is a unit vector now, isn't it? So this is a unit vector, and of course then I can differentiate it again and I get k as to be the r double dash, which is the same thing as the magnitude of t dash, right? Okay, now what I do, what I do is this, in case we have the curve is not a straight line. Now I'm in R3. I'm saying in case the curvature k of R is non-zero. If k, the curvature of this curve R, is non-zero, it's not zero, I define a vector n at S to be 1 by k at S, because now I can divide by k of S multiplied by t dash of S, right? So n of S is 1 by ks multiplied by the vector. Of course, there's a scalar multiplication here, t dash s. Okay, now that means, now since t dash, if I take the magnitude, I have defined now another, now I have got this is unit vector, right, by my definition, because I have chosen a unit speed curve. T magnitude is magnitude of r dash, that's equal to 1. Okay, now with the help of t dash, I differentiate it. So t dash is equal to r double dash, and if I take its magnitude, let me write it again, it is equal to the curvature of the curve at a certain point S. Okay, with the help of this, I defined another vector as S to be, in case k of S is not 0, I define it to be this thing, t dash. Of course, evaluated at S. Everything is being evaluated at a point. Okay, because differential geometry is essentially a local geometry. We are evaluating all these things, t's, n's, and b's at fixed at some point on the curve. Now, if I look at the magnitude, I know that magnitude of t is equal to k, right? Right? Because that's the definition of k, curvature. So therefore, if I have got this magnitude of this vector ns, right, is equal to 1 by ks, the magnitude of this thing, right? But this would be magnitude of ts divided by k of s, but that should be 1, because magnitude of t dash is the same thing as k. So what we got is that I've got now a vector t, then I have a vector which is perpendicular to t, that is n at s. Now t of s, then I have got n of s, and n of s is defined as 1 by k of s into t dash s. And since t is a unit vector, I have a unit speed curve, t dash is perpendicular to t of s, that means n is also perpendicular to t. So I've got two mutually perpendicular vectors that are of unit length, right, provided the curvature is not 0, right? So I've gotten this. Now it's easy now to define another vector which is perpendicular to both the vectors, which is again of magnitude 1. And just take the cross product. So I can define another vector which I denote by b at s to be t at s cross product n at s. Now it would be perpendicular to both vectors, and of course its magnitude would be the product of the magnitudes of the vectors on the right hand side, and that is 1. So therefore I have got a triplet of vectors. I've got a triplet of vectors. Let's call it t. I've got it n, and I've got a b. I've got a triplet of vectors that is defined for each point on a curve, provided the curvature is not 0. Right? So I've got like a local frame of reference for the curve at each point by just differentiating the curve, provided the curvature is not 0 and it's a regular curve, so that I can have that unit speed parameterization in the first place. So that's, we have now come to our basics, right? So I've got a triplet of vectors. Okay, and we choose now remember that if you have t and n, so you have to choose b. Now there are always two choices for b. It is either, now if you have to, how can I show it here? Okay, now suppose this is t, remember that, and this is n, and my plane, of course they are in a plane because they are mutually perpendicular. Two vectors that intersect are always inside a plane. Now suppose the plane is the plane of the paper. Now the choice for t cross n, now b is t cross n. This could be either the vector coming out of the page or coming inside the page, right? We make the choice such that t and b becomes a right-handed system. By that I mean, if this is t and this is n, then b must be coming out of this plane. Yani, I am making a choice that B is like this. If T is this, N is this, then B is coming out of the play. It's just a convention, right? We call it T, and B then forms a right-handed system. It is the same thing as this: T cross N is B, B cross T is N, and T cross N is B. T cross N is B, N cross B is T. Now it should form what we call a right-handed system. We had to make a choice, so we made a certain choice, and we call this, once we make this choice, this is T, this is N, this is B, we call this T and B, which are unit vectors which are mutually perpendicular, defined at each point of our regular curve, of our unit speed curve, and we call this the right-handed system of vectors. Okay, now before moving ahead, okay, now so far we have now for each point I have got this triplet of vectors on a curve. Now so far we have got something nice, one thing is that T dash is equal to K times N. Now this is our definition. This is from where we started. This is how we defined our N, the normal vector. We call T the unit tangent vector, N is the normal vector, and B is called the binormal vector, which is perpendicular to both T and N. Okay, now we came here, we derived this set of vectors by this equation: T dash is equal to K times N. And it is a differential equation. Basically, if I am in R3, this is a set of three scalar differential equations of first order. T dash is equal to K times N. Okay, so now what we have three vectors that are governed, three mutually perpendicular unit vectors at each point on a curve, which are governed by a sort of a differential equation. Actually, we will show that there are three differential equations which we call Serre-Frenet formulae for Serre-Frenet formulae are the three differential equations that govern these three mutually perpendicular vectors that can be defined on each point on a curve. Okay, now let's start what I'm talking about. Okay, now so B is equal to T cross N. That's by our definition, by our choice. So that means if I differentiate B dash, it would be T cross N dash. Using the product rule for the cross product, this should be T dash cross N plus T cross product with N dash. Okay, hence now you must remember T and N are perpendicular, so therefore this cross product would be, I should say T dash and N are parallel basically, so therefore their cross product should be 0, so this is just T cross N dash. They're parallel because N is parallel to T dash. Okay, so it means that now it means that B dash is perpendicular to T, because B dash is now T cross N dash. Therefore, it is perpendicular to both the vectors T and N dash. So in particular, I can say B dash is perpendicular to T. But B dash being a vector of magnitude 1, therefore B dash is also perpendicular to B. So therefore B dash is perpendicular to T as well as B. Therefore it must be parallel to N. So B dash must be some scalar times N. Because in a space you have got three mutually perpendicular vectors, right? T and B, and it is perpendicular to both T and B, so it must be perpendicular. Now we know that another vector which is perpendicular to both T and B is N. Therefore B dash must be scalar times N, and we denote that scalar by minus tau N. Okay, so tau is called, now this is just a convention, we take this minus sign again just to make our calculations, our equations look nice. Now tau is called torsion of the curve R at a point T. So this tau that we introduced it as a scalar here is the torsion. Okay, so far we have, so this is another differential equation that governs our triplet of vectors t and b. Another was, what was this? I had another one. What was that? Huh. Then I have got, इससे पहले क्या था? I had got t dash is equal to k times n. These are two. Then what is missing? It is basically is n dash. Huh? So n dash, we just have to evaluate n dash, and we will get another curve, another differential equation. Let's find n dash before going any further. Okay, now n, you must remember that t and b is a right-handed system, so n would be b cross t. N would be b cross t, and if I want to find n dash, it would be b cross t dash using the different product rule or differentiation. So b dash cross t plus b cross t dash. Now I know that what is b dash and t dash. Huh? So b dash is minus tau n cross t plus b crossed with t dash. What is t dash? T dash is kn. So I would have k times b cross n. I have to maintain the order when I am doing the cross product of vectors, minus tau times n cross t. Now again, using the right-handed system, n cross b is t, but that means b cross n is minus t, so this should be minus k times t. Then I have minus tau, and n cross t, because I'm going in this direction, should be minus b. So that means I've got this n dash. N dash is basically tau b minus kt. So in this way, I've got basically three differential equations, what we call Serif-Rennet formulae,